Hey guys, what's going on? This is Divide and Conquer Math. This is a website and YouTube channel dedicated to helping you learn math on your terms. And this is my study series. So this is really a set of videos dedicated to giving you practice problems to help you prepare for a calculus exam. In this case, we are focused on a calculus exam that has to do with integration. Now, this is the fourth video in my series. And so this problem set is going to look at mixed levels of difficulty. So if you have been kind of practicing and working your way through basic, medium, and hard levels of problems, this is a really great way to see now, if you can throw anything that's thrown your way, make sure that you don't overthink things or that you think things deeply enough. So it should really kind of give you a good breadth of problems. Now, this problem set is only going to be integration problems. In some of the other problem sets, I give you different types of questions. So you might want to just also make sure that you do review some of the earlier problem sets. Don't just do this video if you are looking for more than just straight integration problems. For instance, things like using the first part of the fundamental theorem of calculus, so taking the derivative of an integral, that's covered in some of the previous videos. Okay, so if you've never watched this before, or any of these videos, if you look in the description below, you will find the problem set with an answer key. Now, for the first hour of this video, I am going to be getting prepared to work through this problem set, so you will just see me working. And then after an hour, I'll let you know that time is up. You can work through that problem set alongside me if you'd like. You can then go ahead and grade yourself. Anything that you didn't know how to do or anything that you didn't get right, you can look in the description of this video, and then you will find a little time marker for every single problem. So you can just fast forward to the problems that you want to see. Now, if you realize as you're doing some of these problems that, oh gosh, I forgot how this works and I could really use a refresher of this topic, I also include links to different lessons and examples to help you kind of refresh some of those concepts if you need it. So be sure to check out all those resources. I really strive to make it like a one-stop shop for you guys. Okay, so let's get to it.
Hey friends, if you are not done, I'm going to start doing the problems now. So either pause here or start the study video over, or let's get to it. Okay, so starting with the first problem here. So I have 3 secant x tangent x minus secant squared x. So this is really just a straightforward application of your antiderivative formulas. So if you need a reminder of those, I'll just go ahead and cycle through kind of the list, and you can pause the video if you want to write any of these down. So you can see on this part here, so here's secant squared and secant tangent. So we're just going to use those, but I'll just finish cycling through these. So this is just straight up antiderivative formulas, really. So to finish this one, then this is just going to be 3 secant x minus tangent x, and then since this is an indefinite integral, you just don't forget the plus c. Okay, so for number 2, so I've got now the indefinite integral of 1 over x cubed, and then that's times the square root of 3 minus x squared. So this one does not have some nice antiderivative formula for it. We're going to have to use substitution here. So for this one, so let's see. I just had like a PowerPoint update that is creating all these problems when I write, so sometimes my writing's a little off now. Okay, so my u in this case is going to be 3 minus 1 over x squared, and then my du in this case will be, let's see, negative 2 times x to the negative third dx. And so this will come out to then, let's see, du, this will be 2 over x cubed du. And so when you look at our problem, I have 1 over x cubed, not 2 over x cubed. So I need to get rid of this 2 here. So this will become 1/2 du is equal to 1 over x cubed du. And so now I can substitute this 1/3, oops, sorry, this should have been dx. Okay, so this 1/3 dx can be replaced with this 1/2 du. So let me clear a little space. Okay, so now making these substitutions, so this is going to become the square root of u times 1/2 du, and then I usually just like to rewrite this, so I'll bring that 1/2 out in front. I like to write this as a rational exponent. It just helps me get through the integration part a little faster, I guess. And so this will equal 1/2 times, let's see, so first I always like to figure out the exponent, so I add 1 to this, so this will be 3/2, and then I multiply by the reciprocal, and then this is plus c. So in the end, this will turn into 1/3, 3 minus 1 over x squared to the 3/2 plus c, or you could have all of this over 3, so 1/3, or all of this over 3, tomato. Okay, so for number 3, so I have a definite integral from pi over 4 to pi over 2. So this is cosecant squared x. So this is just a nice straight up derivative formula, actually. So the antiderivative of cosecant squared is negative, let's see, negative cotangent x. And now I just have to evaluate this from pi over 4 to pi over 2. So I've got negative cotangent of pi over 2 minus negative cotangent of pi over 4. So for cotangent of pi over 2, so you might want to bust out the unit circle just to help you with this. But so cotangent, just as like a really quick reminder, the way that my brain kind of thinks about this. So this is cosine of x over sine of x. So I think about that. So cosine of pi over 2 is just 0. So the value of this whole thing is going to end up being 0. And then the cotangent of pi over 4, so that will give me just 1. So this whole thing will just equal 1, and that's it. Okay, so for number 4 here, so this one looks kind of complicated. It's an indefinite integral, and we've got all these things to multiply. So unless you have like just a straight up clear application of an antiderivative formula, then a problem like this is going to require some extra work. Since all of this is being multiplied together, the first thing that you're going to want to do is multiply everything together. So let's go ahead and do that. So I'll have x to the 1/3 times x to the 2/3. So if you add those together, the exponents, I just get x to the first. And then this will be plus 4x to the 1/3 minus 3x to the 2/3 minus 12. Okay, so this I can now integrate, no problem. This is just going to be straight up using the power rule. So to finish this will become 1/2 x squared plus 4 times. Okay, so if you watch my videos, you know that I usually like to figure out the exponent first. So I add 1 to this 1/3, so this will become to the 4/3, and then I multiply by the reciprocal exponent, the reciprocal of the exponent. And then this next part, so this will be 3 times, so again, I'll figure out the exponent first. So if I add 1 to this, this will become to the 5/3, and then I multiply by 3/5, and then minus 12x plus c. So my final answer is 1/2 x squared plus 3x to the 4/3 minus 9/5x to the 5/3 minus 12x plus c. Okay, so for number 5, so I have this definite integral from -2 to 2 of this x minus 3 squared. So one approach that you could take to this is, so you could just go ahead and multiply that all out. So this is from -2 to 2, so this will be x squared minus 6x plus 9, and then I could just integrate this. So this will be 1/3 x cubed minus 6/2x squared plus 9x, and then I need to evaluate this from -2 to 2, and then I can just start plugging stuff in. So let's see, this will become 8/3 minus 3 times 4 plus 9 times 2 minus -8/3, let's see, minus 3 times 4 plus 9 times -2. Okay, so now if I continue to work all of this out, so I will get, let's see, so I have this 8/3 and then this plus 8/3. So I'll write this out as 16/3 because those are my only fractions. So just give me a second to work this all out. So 16/3. And then, let's see, this will become minus 12 plus 18. So this whole thing right here, maybe I'll just note this. This is 6. And then this part here, so this is minus 12 minus 18. So this is going to be -30, this part right here, and then I have this, so minus this -30, so this becomes a plus. So really what I get then is 16/3 plus 36. So if I wanted to keep the fraction going, this would be 36 as a fraction is 108/3. So then this would come out to 124/3, and as a decimal, that's 41.33. So either 124/3 or 41.33, whichever way you got to that. Okay, so for number 6, so I've got another definite integral. So for this one, we're going to have to use substitution because we don't have just a straight up antiderivative formula to use for this. So in this case, so my u will be 3 plus cosine x, and then my du will be negative sine x dx. Now notice in the problem, I have positive sine x, so to turn this into a positive, I need to multiply du by the -1, so I can go ahead and make this substitution. Now this is also a definite integral, so I'm going to want to substitute, or I'm going to want to change out my limits of integration. So if x is equal to 0, then my u, if I plug in that 0, is going to be equal to 4, right? Because cosine of 0 is 4. And then if x is equal to pi, I'm going to have my u equal to 3 plus cosine of pi. So cosine of pi is -1, so then this will go to 3. So now I have this integral going from 4 to 3, changing out my limits of integration. And then this will become, let's see, negative du over u. Okay, so, oh, and I just realized I made a mistake. Sorry, this is 3 plus -1, so this should have been 2. My bad, sorry. Let me change that. Okay, so there we go. So now we're good to go. So now this becomes the negative natural log of u, and I just need to evaluate that from 4 to 2. And so then I can write this out as negative natural log of 2 plus the natural log of 4. And so then there would be your answer, or you could flip-flop the order of them, but that would be it. Okay, so for number 7 here, so I have 4x to the square root of 2 dx. So this one might look very hard, but remember, this square root of 2 is just a number, so this is actually just a straight up application of the antiderivative formula. So if you're like, wait, which formula is this? It's really just like an application of your power rule, right? So my n in this case would be the square root of 2. So you can pause that and read that over if you wish. Okay, so in this case then, my answer will be 4 times. Okay, so I always like to figure out the exponent first. So I know that I need to add 1 to this exponent, right? And then I just take I multiply by the reciprocal of this. So the reciprocal would be 1 over the square root of 2 plus 1. So it's not a beautiful looking answer, but this is actually the answer. So my answer is 4x to the square root of 2 plus 1 over the square root of 2 plus 1 plus c. Okay, so for number 8, this one is also a substitution problem. So in this case, my u is going to be the inside of this cosine function. So actually, let's write this out as not 1 over x squared. Let's write this as x to the -2 minus 7. And then my du in this case will be -2 times x to the -3rd, and then dx. So this is almost what we have in this problem, except this is a positive number, and what I have over here is negative, so I just need to multiply my du by -1, both sides of this by -1. So this will be negative du now equals 2 over x cubed dx, and so there you go. So now, if I substitute these things out, I get cosine of u times negative du. So I can go ahead and integrate this. So the antiderivative of cosine is sine, except now it's going to be negative sine u plus c. So then I just have to substitute my u back in this case. So this will be negative sine 1 over x squared minus 7 plus c. Okay, so for number 9 here, so I've got another definite integral, and so for this one, we're going to want to use substitution again. So in this case, as I kind of look at what my possibilities are, you might think at first that your u should be cotangent, and so this is actually not correct, and I'll show you why. Because the derivative of cotangent in this case, this would be -2 cosecant squared 2x. So this is not what we have in the problem, right? So what that tells me is I'm going to have to use some sorcery, if you will, with rearranging these trig functions. So let's think about this. So this does not work. So let's just think about cotangent for a second. So cotangent of x, this is cosine of x over sine of x. And then let's also just take a moment to think about secant of x. So secant x is equal to 1 over cosine of x. So if I think about this problem then in this context, what I really have here then is cosine the 7th power of cosine 2x over 7th power of sine 2x times 1 over cosine squared 2x. Okay, so you can see then I can make some cancellations here, right? So if I make those cancellations, I get that this becomes cosine, the 5th power of cosine 2x over sine to the 7th 2x. So now I can't do any substitutions with this, but I can rewrite this expression. So let's see, I think I'm running out of space here, so let me clear a little space. Okay, so I can rewrite this as cosine to the 5th of 2x over sine to the 5th 2x times 1 over sine squared of 2x. And now I can rewrite this expression as cotangent, the 5th power of cotangent 2x times cosecant squared 2x. And here is the substitution that I can make. So there's a little bit of sorcery to get to this. So let's restate this problem now as this expression here, because then I can finally get to the substitution part of this. So just using this part that we just talked about as my guideline. So my limits of integration stay the same, and then this is the 5th power of cotangent 2x cosecant squared 2x dx. Okay, so now we can work on the substitution. So I'll clear some space. And my u in this case, my u is going to be cotangent of 2x. So then my du is negative 2, don't forget to use the chain rule here, negative 2 cosecant squared 2x, which would make my du negative, I'd want to manipulate this and rewrite negative du equals 2, oh, sorry. Okay, sorry, I need to divide out this negative 2. That's what I meant to do. So to just rearrange this, this is negative 1/2 du equals cosecant squared 2x dx. So dx there. So now I can substitute out this part here and this whole part here. And I want to just switch out my limits of integration while we're at it. So now if my x is equal to pi over 4, then my u of the cotangent of, let's see, so 2 times pi over 4 is going to give me really pi over 2. So the cotangent of pi over 2 is just going to be 0. And then if x equals pi over 3, then my u of cotangent of, let's see, this will be 2 pi over 3. This is going to equal, using the unit circle to get to this, this will be negative square root of 3 over 3. Okay, so now let's go ahead and clear some space. See, I got to clear a lot of space. So let's just start with a new slide entirely. So using the information that we were just talking about. So this is going to go from the negative square root of 3 over 3 to 0. So using my new limits of integration. And then this will become u to the 5th times negative 1/2 du. So that's using all the information that we came up with in this previous part. Okay, so now, let's see, I'll bring that negative 1/2 out in front. And I will go ahead and integrate. So this becomes negative 1/2 times 1/6 u to the 6, and I need to evaluate this from 0 to the negative square root of 3 over 3. I did not change the order of my limits of integration. I'm fine with it. I can just plug them in as is. So this will become negative 1/12, and then negative square root of 3 over 3 to the 6 minus 0. Now, just to walk you through the algebra of this, if you really wanted to like go through and find the fraction, it doesn't take that much time. So this will come out to negative 1/12, negative 1/12. Okay, so think about taking this square root of 3 to the 6. So I can simplify this then to 3 to the 6 over 2, right? So writing it in its rational form. And then this part here will be 3 to the 6. So let's simplify this. So this becomes negative 1/12 times 3 to the 3rd over 3 to the 6. So really what I'm looking at here then is negative 1/12 times 1 over 3 to the 3rd. So this will equal negative 1 over 324, which as a decimal is this 0.003. So there would be your final answer. Okay, so for number 10 here, so I've got another definite integral. And this one I can just actually just integrate right as it is. So if you're not sure what to do with like this e to the negative x, so there are actually integration formulas to help you work through that. So I'll just pop up one of those integration formulas. So I've got e to the kx, so then the antiderivative of that would be 1 over k times e to the kx plus c. So this is just the antiderivative structure. So if I wanted to actually use that in my problem, so I would write this as the natural log of the absolute value of x minus e to the negative x. That's how that would work out. And then I would just have to evaluate this from 1 to 3. So let's go ahead and work this out then. So this becomes the natural log of 3 minus e to the negative 3rd. And then it would be this minus the natural log of 1 minus e to the negative 1st. Now, the natural log of 1 is just 0. So this becomes the natural log of 3 minus 1 over e to the 3rd plus 1 over e. So that would be the answer. Okay, so moving on to number 11 here. So I have this big crazy looking integral, but this is really just an application of substitution, because you'll notice, so if I were to set my u equal to this thing that's being taken to the 7th power, so just explore with me a little bit here. So I've got x cubed plus 3x squared minus 3x, so there's my u. So my du then would be 3x squared plus 6x minus 3. Okay, so you might be saying to yourself, and then dx. Okay, so you might be saying to yourself, oh, but this is not equal to this. But notice if I just multiply all of this part by 3, I will get to this part here. So if I multiply both sides of this by 3, I get 3 du. This will equal 9x squared plus 18x minus 9 dx, and then we're in business. So let's go ahead and make these substitutions. Oh, let's also do the limits of integration. My bad, sorry. So then, let's see, if my x is equal to 0, then my u will be equal to 0. And if my x is equal to 1, then my u will be equal to, let's see, if I plug 1 into this, I get 1 plus 3 minus 3, so this will actually still just equal 1. So the limits of integration in this case actually do not change. So I go from 0 to 1. This becomes u to the 7th times 3 du. So if I work this out, this becomes 3/8 u to the 8th. And then I can just go ahead and evaluate this. So this becomes 3/8 minus 0. So at the end of the day, my answer is just 3/8. Or if you wanted the decimal version, 0.375. There you go. Okay, so for number 12 here, so I've got 1 minus cotangent squared x. This is a pretty standard integration technique, actually. So we do not have an antiderivative formula for cotangent squared. So instead, what you use then is you think about some of your Pythagorean identities. So in this case, I am thinking specifically of this Pythagorean identity. So if I were to use this, then if I just rearrange this, I can get that cotangent squared theta is equal to cosecant squared theta minus 1. So I'm going to substitute this into my cotangent now. So this will become 1 minus cosecant squared x minus 1 dx. Okay, so then I get 2 minus cosecant squared x dx. So now we just work this out. This becomes 2x. So the derivative of, or the antiderivative of cosecant squared is tangent x. Oh, sorry. No. Cotangent x plus c. And that would be it. Okay, so number 13 is very similar to number 12 in that we don't have an antiderivative formula for tangent squared x. So we have to use a Pythagorean identity here. So in this case, that identity is going to be 1 plus tangent squared theta equals secant squared theta, or I could rewrite this as tangent squared theta equals secant squared theta minus 1. And so then I can make that substitution, or I can change this integral. I can't speak. Okay, so now I'm going to rewrite this as secant squared x minus 1. This I can totally integrate, right? So the antiderivative of secant squared is tangent. So it'll be this minus x. And then I just need to evaluate this from pi over 4 to 0. So this will just end up being tangent of pi over 4 minus pi over 4, and then the rest of that will just be minus 0. So this comes out to 1 minus pi over 4. So that would be your answer. Okay, so for number 14 here, this is a pretty classic substitution example. So in this case, my u will be the natural log of x, and my du will be 1 over x dx. And then I also want to change my limits of integration. So if x equals 2, then my u will be the natural log of 2, and if my x equals 3, then u will be the natural log of 3. So I can go ahead and make these substitutions then. So this becomes the natural log of 2 to the natural log of 3, so changing my limits of integration. And then I have u du. Nice and straightforward. So now, this will be, oops, sorry, this should be 1 over u, gosh. 1 over u du, that's what I meant to write. All right, so now if I integrate this, this becomes the natural log of u, and then I just have to plug in these limits of integration. So this answer looks a little weird, but it's totally right. This will be the natural log of 3 minus the natural log of 2, and there you go. Okay, for number 15, I've got an indefinite integral. So this one actually is pretty straightforward in that I can break this up into pieces to make my life much easier. So this will become 1/2 plus 1/4 cosine of 4x. And now I can just use my standard integration or antiderivative formulas to finish this. So this will be 1/2 x plus 1/4 times 1/4 sine of 4x plus c. And so then my final answer will be 1/2 x plus 1/16 sine of 4x plus c. And so that's just a standard antiderivative formula. Okay, so number 16, so this is a pretty classic just substitution problem. So I'm going to set my u equal to x squared minus 6, and then my du will be 2x dx. Now notice in this problem I have x dx, not 2x, so I need to divide both sides here by 2. So I'll have 1/2 du equals x dx. So if I substitute now, I will get 1 over u to the 7th times 1/2 du. So now I just want to restate this as 1/2 u to the negative 7th du. And so then this will become 1/2 times. So remember, I always like to first add 1 to my exponents. This becomes, if I add 1 to negative 7, this becomes negative 6, and then I multiply by the reciprocal. It's just how I like to do it. Okay, so now I've got this all set up. So my final answer, let's see, I'll write my final answer over here so you can see it nice and clearly. This is negative 1/12 over x squared minus 6 to the 6 plus c. So that would be your final answer in this case. Okay, so number 17 is another indefinite integral here. So this is another case of substitution. So for this one, my u is going to be 1 minus 1 over x. I'll write this as x to the negative 1. So then my du will be just x to the negative second dx. So this one's pretty nice in that we can just go ahead and make these very simple substitutions, but this one does have a little bit of a plot twist. So I go ahead and I substitute. So I get cosine squared u du, and now, boom, here's a new problem. We have to integrate cosine squared, and we don't have an antiderivative formula for this. Also, the Pythagorean identity won't help us because I don't have an antiderivative for sine squared. So in this example, when you have cosine squared or sine squared, you have to use the half angle identities to help you with this, which is cosine squared of theta over 2 is equal to 1 plus cosine theta over 2. Now, sometimes when you Google this, by the way, they show you the version with the square root, and you can just manipulate it so that it's the squared version. That's all I did for this, but a lot of students ask me about that. Okay, so I need to rewrite my problem then as cosine squared, let's call this now 2u over 2 du, so that I can implement this formula here. So this will now become 1 plus cosine 2u over 2 du. Okay, so now I can integrate this. So let's see, I need some space, so I'll clear some space. Okay, so now let's write this out as 1/2 plus 1/2 cosine of 2u. So I just have to integrate this. So this is 1/2 u plus 1/2 times 1/2 sine of 2u plus c. So my final answer will be 1/2 1 minus 1 over x plus 1/4 sine of 2 1 minus 1 over x. And all of that is together plus c. So it's kind of a crazy answer. And then you could simplify this farther. So I've seen different ways that this was simplified farther, but I'm actually just going to leave it like this for now. Okay, so moving on to number 18. So this one is just using your standard antiderivative formulas, but I think these ones are kind of commonly forgotten. So I will just pop those up. So I'm going to use this antiderivative formula here. And then this 3 to the x has this antiderivative formula here. So literally just standard antiderivative formulas, but I just threw this one in here because I knew that these ones are very commonly forgotten. So just applying those formulas, this will become negative e to the negative x. And then this other part, this is going to be 1 over the natural log of 3 times 3 to the x, all of that plus c. And so I could rewrite this as, let's see, if I wanted to rewrite this, I guess I could write this as 3 to the x over, negative 3 to the x over the natural log of 3 minus e to the negative x plus c. But that's it really. Okay, so for number 19, so this one might look very tricky and like maybe you've got to use substitution, but this is actually another one that's just a straight up antiderivative formula. So that's why I threw this in here. This is another really commonly forgotten antiderivative. So I've got k squared x squared minus 1, this square root of k squared x squared minus 1. So if you look at the problem I have here, so this is my k squared, what's in that place is 9. So this is really 3 squared, right? X squared minus 1. So this perfectly fits this antiderivative formula. You can pause the video to convince yourself if you need to. So this is just straight up applying the formula then. This will be 1/3 inverse secant 3x plus c. So it's just kind of a reminder to go back and study those if that's something that is covered in one of your classes, because these ones are super, super easy to forget, I think. Okay, so for this final problem, so the only way that you can do this last one is you've got to multiply everything out. So let's start there. So I multiply this out, I get cosecant squared x plus 2 cosecant x cotangent x plus cotangent squared x dx. Okay, so now you've really got to be on top of your antiderivative formulas for this one. So I'll just give you a brief reminder. So cosecant squared x, we can integrate this. This one has an integration formula, as does cosecant cotangent. So those two we can integrate in this problem. So what I'm saying is this part has an integration formula, as does this part. Now, there is no integration formula for cotangent squared x, so this is where we have to use that trick with the Pythagorean identity. And the formula that we want to remember in this case is 1 plus cotangent squared x equals cosecant squared x. So we're going to use that to help us with this. Now, these first two parts I can definitely integrate. So this will be cosecant squared x. So this antiderivative is negative cotangent squared x. And then I'll just keep color coding this. So 2 cosecant x cotangent x dx. Oops, I'm sorry, I forgot the dx in the other one. Okay, so this is negative 2 cosecant x. So those two are no problem. Now for this last problem, so this cotangent squared x, the only way you can approach this one is by rewriting it as cosecant squared x minus 1. So by using this Pythagorean identity. And so that then will equal negative cotangent x squared minus x. So now I have all the pieces of this, so I just have to kind of put them all together. So let me clear a little space here so we can finish this problem. Okay, so now putting everything together, so I've got negative cotangent squared x minus 2 cosecant x minus cotangent squared x minus x plus c. You only need one plus c in there. You don't need to put in like 3 c's, by the way. So the final answer here is negative 2 cotangent squared x minus 2 cosecant x minus x plus c. And so there is the final answer. And so that wraps up this video. Hope it was helpful, guys. I have one more video after this on how integration works with area and Riemann sums. So if you're looking for some practice on that, check out the next video. Feel free to leave me a like or hit the subscribe button, and thanks for watching, guys.